Okay, because some students missing. Please, I want to share the videos there.
In the interest of time, the work they have done to just prepare it, have to settle those down, so that it's also going to be a good learning for us as well. So, and also let me tell you, before sir begins, these sort of data collection you people can also do. You can actually take photographs of all these experiments in your IA.
Yes.
It adds into your personal engagement. When you are showcasing something which is being done by you, it adds as a component of that personal engagement. So I can't remember last time in maths department even thought of doing something like this. So I really appreciate the effort that was taken by you and sir.
Yes.
I was also on the learning.
Hello students, welcome to the collaborative class with me, the mathematics teacher and my department colleagues, along with the physics teacher, Mr. Gyaneshwar. Today we have come here to collaborate the use of math in physics and use of physics in math, either way. So we will be collaborating the class with learning how these experiments will make us understand the trigonometric graphs which are generated, like the sine curve, cos curve and the tan curve, which we have learned in the mathematics class. We will see how basically they are generated through different experiments. So today we will demonstrate two experiments out here, and then we will also learn how trigonometric modeling is done. So trigonometric modeling is a concept where whatever graph you get, you can find its equation using certain softwares. And you can collect the data using the data logger. So these are the things which you're going to learn for today, which helps you even in your explorations, along with the learning of math and physics and the applications of the subject in real life. So over to Mr. Gyaneshwar. Please take on from.
Okay. So see, in real life, whenever you find that there is some restoring force which brings an object back to its equilibrium position, you find that it can be modeled using simple harmonic motion. So the equation is like this. See, if the acceleration of any object, you know, it will be proportional to the net force acting on it. Agreed? It takes place in the direction of net force, and it will be equal according to Newton's second law. So it will be net force by mass. Agreed? Now for simple harmonic motion, the condition is this net force should be proportional to the displacement from its equilibrium position. So equilibrium position is defined as a position where the net force is 0. So right now the net force acting on it is 0. So can you tell me what are the forces acting on this mass right now?
The tension from the spring, tension of the spring and gravity.
Okay, so gravitational force is acting in which direction? Okay. So in this case, mg is downwards, and let us call this spring force Fs is upwards. Both are equal, cancelling out, and so net force is 0. So this is the equilibrium position. Now this position I am going to call it as 0 position. So this is the y-axis. So this is y equals 0. Okay, and this will be the time axis. So right now it is at 0 position in y-axis. If I displace it from its equilibrium position, say by pushing it up, what will happen to the net force? The spring force will become more or less. Right now it is stretched. If I push it up, what will happen? Less. But the weight will be same. So if the spring force becomes less, but the weight is same, more, so net force will become more. It's a vector sum. Agreed? So the acceleration will be in the downward direction. So if I move it up from its equilibrium position and release it, it will start accelerating downwards, and then it will set into simple harmonic motion, vibrating about its mean position. So now let us see that how that position changes with time. Okay? So what I have done is I have kept a motion sensor below it. So see how technology is used. This emits ultrasound waves, which we can't hear. The sound waves will hit this card and bounce back. So it takes some time to reach back to this sensor. So using that time taken and knowing that speed of sound is around 340 meters per second, it calculates this distance. So as this distance changes, the software will tell me the position. Okay? So this graph will give me the position versus time as it keeps changing. So initially this distance I will reset, I will calibrate it to 0. So whatever is this distance, that will be set to 0. So this software which you see on the screen is called loggerpro. So this sensor is detected by this software. So that it will read the data. So go to this experiment and click on the 0. So it's just calibrating it to 0 now. Okay? Now simultaneously this sensor will plot the acceleration and velocity both with time. Okay? So now I set it into motion. And I will collect the data. So now initially you may panic thinking that nothing is detected, but actually we have to adjust the scale of the graph. So we have a function called auto scale. So if you look here, this alphabet A is written. So I select each graph and click on it, it will scale it up. So if I select acceleration and click on it, it will scale it up. So do you see? I have already fit the function also. So the way you do that is, once you have the data collected in form of red lines, just click on this button after selecting it, curve fit. So I'll just show it to you. You click on it, you will get this curve fit and see how many functions you can fit to it. So I have selected a sine of bt plus c plus d. So it's a sine function. I can also fit a cos function. So it will just vary the phase. The c part will change. This is actually cos squared. Then when we do damped harmonic, we can use this function a into e power minus bt. So this a into e power minus bt, what it does is it will reduce the amplitude with time for damped SHM. For that I have a second demonstration. So for example, if I displace it like this, its amplitude reduces very quickly due to the drag force exerted by the air. So that we will model using the second function. Okay, now let's first see how.
1 second.
Yeah.
Now coming to the mathematical part of this, as sir told that there are different functions which are shown there. The fit, the best curve fit. It is exponential, it's trigonometric, logarithmic, many functions are there. So how do you know which curve is best fitting this shape? It is all based on the correlation coefficient which you find here. In the software, if you fit the function, then it will show how better it can fit using the correlation value. If it is very close to 1, that means it's a very good fit. If it is very far away from 1, then it is not that good fit. So which do you find is the nearest value to 1, then that is a very better fit. I think 0.0090. So this is a perfect fit for the given data. So even when you collect the data of your own in your exploration and you try to fit in some curves, what you do is we use these kind of softwares and then try to see which is the best fitting curve, whether exponential or quadratic or trigonometric, and you justify that purely mathematical using the regression analysis which you're going to learn in statistics, and that is where you'll learn about correlation. So these are the concepts which we use in the exploration or data collection. It's a purely realized model. Even in today's world we use this very much. So over to you. Thank you.
Just to add one more, sir, even as students, you can even then get your own points and also see manually how close you are to this model. So this model has been verified through software. You can even check by your own SHM model whether that model and this model are very close to each other. So is this software free?
Yeah,
Actually, we have the CD.
CD is there, sir. It's not free, but
So you can just take the CD. It will be actually having an old version, but once you install it in your computer and then use online update, it will update to the latest version. So that way it is free right now. School has purchased it, and you can have any number of copies.
So this can be obtained from
Our physics lab. From server room also they have made a copy. So you just tell server room to install it in all their laptops, they will install it. So once you install the version given by a server room, then do online update to get the latest version.
the benefit, most of the benefits with this software is that there is video synchronization. Even you can attach a video, and suppose I am shooting a basketball, and I record my own video of a basketball shoot, I put it there in video synchronization. I can select the points of my basketball shoot and I can generate a quadratic flow on that.
Yes.
So that is one of the best thing about this.
So
I have the software, sir. I shared it.
So one more software is Tracker. Tracker is another software for video analysis. Okay, so now the thing you need to notice about the data fits is, this is describing the change in position, change in acceleration, change in velocity with time. All of them seem to be modeled by sine function only. Then what is the difference in the equations? Just see. It's a sine of some bt plus c, right? And then plus t. This plus t is just to adjust for any offset. So suppose this oscillation happened at around an equilibrium position which is at plus 10. So that offset would be given by d. So right now, is it having any offset? All these graphs are having equilibrium position at 0 only, right? So that sign variation is happening around 0. So the d value should be how much in all the cases?
Almost close to negligible.
Negligible, close to 0. So check whether it is true. It's 0.0006, 0.011, again 0.008. So its d is practically negligible. Okay. Then what about A, amplitude? In amplitude of position is supposed to represent what? So this is around 2 centimeters. Why should it be 1?
1 meter.
1 meter?
No, it's according to the sine function. No.
Now think. Amplitude is supposed to determine, it's supposed to show the maximum displacement from its equilibrium position. So when I displace it like this, how much do you think it moved from its equilibrium position? This much? Around 1 or 2 centimeters? So now you see here, this is 1 centimeter, 2 centimeters. So it's actually showing you the maximum displacement from its equilibrium position.
Or the distance from the principal axis.
From distance from the equilibrium position.
Principal axis.
Y equal to 0 position.
That's where you drew the line.
So if I now repeat the same thing with a bigger amplitude, then in my fit, this amplitude value will change. But will the periodicity change? So which constant is capturing the periodicity? That is, how much time it will take to repeat its pattern? B. So now, in one cycle, position, velocity, acceleration, everything repeats its value in one cycle. So do you think in all these three equations, the B value will be same or different? It has to be same, because all of them repeat its motion every one cycle. After every cycle, it repeats its motion in the same way, right? So B value has to be same. So check it. What is B here? 13.04, 13.02, 13.04. So all three have the same periodicity. Okay, now question for you. If I want to change the B value, what should I change here? If I want to make this, suppose in 1 second, right now I have 1, 2, almost 2 cycles in 1 second. Suppose I want to make it less. I want to have less than 2 cycles in 1 second. Make it oscillate slower.
Smaller than string or weight?
Weight should be
Weight should be more.
more or less?
Less.
Less.
Why less?
More.
Okay, so if the weight is more, it will have more inertia, right? So the spring force will be able to change its motion easily or with more difficulty? More difficulty. So every time it has to make it change direction and come back down, change direction, go back up, it will struggle to do that. So if I increase the mass, the frequency should become more or less? Less. So now it's difficult to increase the mass, it's easier to decrease the mass. So let me decrease it. So what do you expect the frequency to do? Become more. So the B value should become
More than 14.
more or less.
More.
If B is more, what will happen?
Sir, can I just make one more statement? For the boys who are going to do calculus, if you look at the position graph and the velocity graph, look at just the first thing, so much more can be added. we'll be talking about maximum, minima, double derivatives. All these graphs
lot of
really
calculus comes
also
in.
tells you which side is positive, why is double derivative negative for minima. All of these concepts can be shared. I really feel that through this graph, a lot of concepts just becomes quite easy.
When we do calculus, again we will come back here.
We'll come back to this.
Once again. See, one thing you have to understand here, as sir was telling very clearly, thank you sir, these things what we learn in class are called transformation of graphs, right? Dilation, reflection, translation is what sir is explaining in the concept of frequency and amplitude, okay, or the period of the graph. Now one more thing, it's so interesting to see that the spring is moving up and down, right? But the graph is coming like this. So what is the connectivity you see there? I just want to ask this as a question. The graph is moving vertical, the weight is moving vertically, but the graph is propagating horizontally. Can you explain the difference between them?
Time.
Yeah, with changing time, you are seeing an oscillation which is having max and min, which is equally repeating. Okay, so that is how we have to understand. Because many a times, we feel that because it is moving vertically, the graph should also be vertical. But that's not the case because we are looking in terms of velocity time graph, acceleration time graph, and position time. But when you do calculus, as sir said, definitely we will come because there are more things to explain.
Okay, so make your predictions. Reduce the rate. So you expect it to oscillate more times per second or less times per second? More. So what change do you expect this B to do? B should become more or less? Just think. This inside the bracket, what you have is angle at any time t. Okay? Now time will increase at a steady rate, fixed rate. Now how can you make the angle increase at a faster rate?
Use dilation, horizontal
You
stretch.
should multiply something with time and it gives rise, okay, let's make it simpler. Let's say this phase is a constant and let us say this constant is 0. Now tell me, if time is going to increase by 1 second, but you want the angle to increase by a greater value, you can't change the rate at which time increases. So how can you make more angle to be covered in the same time? You can't change time value, but you can change the constant which is multiplied with time. Are you getting what I'm saying? That constant is B in your fit.